So can I start? Okay.
Yes, please do. Yeah.
Thanks a lot, first of all, to the organizers for inviting me to give a talk at this workshop. And in this talk, I would like to present results of several works which I did with my collaborators. And in these works, we studied model properties of certain BPS indices, which count black hole states in Calabi-Yau string compactifications. And we didn't just study the properties of these guys, but we actually used them to compute these BPS indices. And this is what I'm going to explain you. But first, let me start from explaining the general setup which we considered and posing the problem which we tried to solve. So let's consider type 2A string theory on a Calabi-Yau threefold. And then, of course, in 4 dimensions, we get effective theory, which is given by n equal to supergravity coupled to some number of vector and hypermultiplets. And in this theory, we can define BPS indices, which count, BPS states with a sign of a given electromagnetic charge. This charge has two B2 plus 2 components, where B2 is the second Betti number of the Calabi-Yau, just because we have B2 plus 1 gauge fields in this theory. So B2 of them come from vector multiplets, and one additional comes from the gravitational multiplet. And of course, each gauge field gives one electric and one magnetic charge. So for me, P0, Pa will be magnetic charges, Qa, Q0 will be electric. And P0 is associated with this graviphoton, and Pa, Qa with the vector fields from vector multiplets. And these BPS indices, they have both physical and mathematical incarnation. Namely, from the physics point of view, as I already mentioned, they count the states of half BPS black holes appearing as solutions of n equal to supergravity. And at the microscopic level, the same black holes can be interpreted as bound states of D6, D4, D2, D0 branes, wrapping respectively 6, 4, 2, and 0-dimensional cycles on the Calabi-Yau threefold. And what's nice is that these charge components, they precisely correspond to these d brane charges. So P0 is D6 brane charge, for example, Qa is D2 brane charge, and so on. And on the mathematical side of the problem, so these BPS indices, they have been conjectured to coincide with the so-called generalized Donaldson-Thomas invariance of the Calabi-Yau. And for mathematicians, it's a really great challenge to compute these guys. And probably at this workshop, I shouldn't explain why these BPS indices are important from the physics point of view, but okay, let me mention just that, of course, they give entropy of black holes, which we're all very interested in, and also they appear as they parameterize the non-perturbative contributions to the effective action, for example. So therefore, they are really important. And if we consider it a non-compact Calabi-Yau, then we could use many different techniques to compute these BPS indices, such as localization, quivers, relation to some topological theories. But once we are not on a compact Calabi-Yau, most of these techniques just don't work. And it's really a very hard problem to compute these BPS indices. But nevertheless, let's try. So I will actually consider mostly concentrating this talk on a certain subset of these BPS indices, which correspond to D4, D2, D0 bound states. So in other words, I put my D6 brane charge equal to 0. And the corresponding DT invariant is called rank 0 DT invariant. As you can get, the rank here simply means the value of the D6 brane charge. And this particular subset, D4, D2, D0, they possess some nice, the so-called spectral flow symmetry, which allows to little bit reduce the dependence on the charges. So the BPS index will still depend on the full D4 brane charge. Also, there will be dependence on D0 brane charge, or more precisely on its kind of shifted version, which I denote by Q0 hat, and which stays invariant under this spectral flow symmetry. But what is important is that instead of the full dependence on D2 brane charge, there will be dependence just on the so-called residue class. And it's important because this guy takes only a finite number of values. And namely, it takes this number is equal to the determinant of quadratic form constructed from the intersection numbers of the Calabi-Yau and the D4 brane charge. And therefore, I can denote my BPS index as index labeled by D4 brane charge, this residue class, and it depends on this invariant D0 brane charge. And after that, I can sum over this Q0 hat and get a generating function of these guys, which is labeled by D4 brane charge and this residue class mu. And you can interpret this residue class mu as a kind of vector index. So in other words, this generating function HP will be a vector valued object. And the number of components is given by this determinant of kappa AB. Just one important comment is that actually we consider generating functions not of the original integer valued BPS indices, but of the rational version. And this is because it's expected that once you consider generating functions of these rational values, then these generating functions will possess nice modular properties. I'll explain you later where these properties come from and how they look like precisely. But at this point, let's just consider the most simple example where D4 brane wraps an irreducible divisor.
Hey, can I ask you a question? Sorry, Sergey. Yeah. What is Q0 max? How does it arise?
Yeah, okay, indeed, it's important for the being able to define this generating function that Q0 hat is bounded from above, and it comes from the so-called Bogomolov bound. So it's a general mathematical property of DT invariants that they vanish if this bound is violated. So it was proven by mathematicians long ago, and it's well established. So let's return to our simple example of a reducible divisor, which means that we put our D4 brane on a 4 cycle, which cannot be decomposed as a sum of other 4 cycles. And in this case, it has been argued already many years ago by Maldacen, Strominger, and Witten that this generating function must be a weakly holomorphic vector-valued modular form of this particular weight determined by the second Betti number. So let me explain what these words mean. So weakly holomorphic just means that when I expand my generating function in a Laurent series in Q, so which is an exponential of 2 pi tau, then my series will have a part with negative powers of Q. There will be a finite number of such terms, but they must be present. So in other words, this n mean is less than 0. Or in other words, Q0 max is larger than 0 here. And then a vector value just means that we have this vectorial index mu, and modular of this weight means that under the standard model transformations, we get this standard factor c tau plus d to the power of the weight. And here we get just, since our function is vector valued, we get a rotated version of this guy, where this matrix M mu is called multiplier system, and it's well known. So it's some fixed representation of a finite dimensional representation of SL to Z.
I'm sorry, question.
Yeah.
Is the mu in HP in mu the same as the residue class mu? Or
yes, yeah, it's the same mu.
So I sort of lost a bit of intuition. Can you say something more about the residue class, please? Because my internet got stuck.
So where it comes from?
Yeah.
There is the spectral flow symmetry, which says that, roughly speaking, your BPS index is invariant under certain shifts of the charge vector. And these shifts allow to essentially remove the D2 brain charge, but not completely. So some information about it remains. And then because it turns out that this spectral flow so the D2 brain charge lives in H2 and the spectral flow parameter lives in H4. And if these two lattices are not the same, then you cannot completely remove the D2 brain charge.
So it's H2 of the Calabi-Yau manifold.
Yes, yeah,
okay.
Yeah, of course, yes. So it's just if your H4 is H2 is your lattice, then H4 is your lattice, then this is the standard factor dual lattice divided by the original lattice.
And mu is then
an element of this residue group.
Okay, and the cardinality of this residue group is then just the cardinality of H4 minus, sorry, the rank of H4 minus the rank of H2, or?
No. You have to compute the determinant of the quadratic form.
Okay.
Assigned to your lattice, and the claim is that the cardinality of this residue group is equal to the determinant of this quadratic form.
I see. So the determinant of the quadratic form is 1 if it's self-dual? So you're not taking self-dual quadratic forms, or?
Well, I can consider also the case where determinant of this quadratic form is equal to 1. But for example, let's consider one-dimensional case. Yeah, okay. This is the most simple one. Namely, this is what I will consider in the following. Namely, when the B2 is equal to 1. So 1 Keller modulus. Then this quadratic form is just a number. So it's kappa times P, D4 brain charge. So you see, so you can get determinant equal 1, but for this you need to take Calabi-Yau with intersection number equal to 1, and D4 brain charge also is equal to 1. So it's a very, very special case.
Okay. And just the quadratic form that you write out, it's in how many variables now?
What do you mean?
So is it binary quadratic? Is it ternary quadratic? It's some. So A's. Sorry. Okay, no, sorry. Got it.
Runs from 1 to B2.
1 to B2. Okay. Okay.
Yeah.
Sorry. Thank you.
Okay. So we consider this simple example, namely, there is a claim that generating function for irreducible divisors must be a weakly holomorphic vector-valued model form. And there is a beautiful fact that the space of weakly holomorphic model forms is finite dimensional. And moreover, this dimension is bounded from above by the number of polar terms, namely those terms which in this series have negative power of Q. And this means that if you somehow manage to compute the polar coefficients, or the coefficients of these polar terms, then you can restore the full generating function. So just if you find finite number of coefficients, you can get the full function which contains information about infinitely many invariants. And precisely this, we realized this program 2 years ago with Sahelov, Fisbach, Albrecht, Klem, Boris Pelin, Torsten Szymanek, for a family of one parameter Calabi-Yaus, and namely we did it in a kind of one can say in a consistent way, in the sense that we developed certain procedure how this can be done. So let me briefly explain how it works. So we started with the topological string theory defined on our Calabi-Yau manifold, and as you know, the partition function of this theory is captured by Gopa-Kumar-Vafa invariance. So if you know this partition function, you know this GV invariance. And there is a way to actually find this topological string partition function by the so-called direct integration method, which is, roughly speaking, you solve the holomorphic anomaly equation for the partition function, impose certain boundary conditions which allow to fix the holomorphic ambiguity. And in this way, you find GV invariance genus by genus. Once you know GV invariance, you can apply the so-called MNOP formula due to Maulik, Nekrasov, Okunkov, and Podkhripande, which allows to compute from GV invariance rank 1 DT invariance. In our terms, these are D6, D2, D0 BPS indices. And then Soheilov-Isbach derived some nice wall-crossing relations which allow to compute from this rank 1 DT invariance our rank 0 DT invariance. And following this procedure, we managed to compute all polar coefficients for several Calabi-Yau threefolds, compact Calabi-Yau threefolds. And this way we get precise expressions for the generating functions of our rank 0 DT invariance. And at this point, you can actually go back, and because now you know infinitely many rank 0 DT invariants, just using the same wall-crossing relations, you get rank 1 DT invariance, and you can derive new GV invariance. And this is very important because the direct integration method is actually, it cannot go up to arbitrary genus, because the number of known boundary conditions for fixing the holomorphic ambiguity of topological string grows slower than the number of required boundary conditions to fix this ambiguity completely. So at some point you are just stuck and you don't have enough boundary conditions to solve topological string. And our procedure actually allows to get new boundary
Time
conditions.
left, 7 minutes. What is this?
Sorry?
It's the amount of
Yes.
time you can stream on YouTube.
Can I continue?
No, 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 no. No, no.
Brilliant.
I think it's not on the chat. It's upstairs on the bar. It says next to the YouTube blinking link. It's saying time left 6 minutes.
And should I stop? Oh.
I don't know. Sorry. Maybe just give them time to
Yeah.
figure out what's going on.
Seems like YouTube doesn't work.
It's until 7 p.m. Why is it giving me this stupid warning?
Gabriel, can I continue? Or?
Sorry.
Yeah, I think you can continue, Sergey.
Yes, I think you can continue, Sergey.
Okay.
Yes, sorry. We have an issue here, a Zoom issue. Please go on.
Okay. Okay, so where was it? Yeah, just that this procedure allows to compute additional boundary conditions for topological string, and in this way we can overcome the limitations of the direct integration method. So this is all nice, but the next natural question: can we generalize this to arbitrary divisors, arbitrary de Forbin charge? And it is this question which I would like to address in this talk. So this is the plan. So first, I will explain you the origin of modular properties, and you will see that for more complicated cases, they're also more complicated, namely there will be certain modular anomaly appearing. And then I will concentrate on the simplest non-trivial case, which corresponds to mock modularity, where we can solve the modular anomaly, then we can find the corresponding polar terms and find precise results for BPS indices. In the second part of my talk, I wanted to consider even more complicated case of kind of arbitrary de Forbin charge, where we cannot still find the polar terms and the corresponding BPS indices, but at least I'll show you how one can solve the modular anomaly in such situation. Okay, so first, let me explain why these generating functions should possess any modular properties at all. Well, you remember we are considering type 2A in the Calabi-Yau, which is the same as M theory in the Calabi-Yau times the circle. Let's compactify this setup on an additional circle. Of course, then we go to 3 dimensions. And in 3 dimensions, our effective theory can always be reformulated as certain supersymmetric nonlinear sigma model with some target space, which I call M. And now you see that in the M theory setup, we have the product of 2 circles, which is torus, and hence we must have the modular group SL to Z in the game. And indeed, one can show that this target space must carry an isometric action of this modular group. And the same conclusion you can get if you work in the T-dual setup. So you do T-duality along this circle S1. So you find yourself in type 2B, and in type 2B there is S-duality. And then this target space M appears as a hypermultiplet modular space and should carry the same isometric action of S-duality. Now, we're considering D4 branes wrapped on a 4 cycle. So since D4 brane has 5-dimensional volume, walled volume, this leaves still 1 dimension uncompactified, and let's also compactify it on this additional circle S1. So then all dimensions are compactified, and we get, from space-time point of view, kind of point-like object, which of course can be interpreted as an instanton. And these instantons, they do affect the theory, namely they affect the metric on this target space M. So they induce certain instanton corrections to the metric tensor. And moreover, these instanton corrections, as already mentioned in the introductions, they are weighted by the BPS indices, omega or gamma. But the good news is that we know how to compute all these instanton corrections. So we did it 15 years ago already. So there is kind of twistorial construction of a full non-perturbative metric on this target space M. So you see, what do we have? We have a metric which depends on these BPS indices through the instanton corrections, and on the other hand, must carry an isometric action of SL to Z. Of course, this cannot happen for arbitrary BPS indices, and SL to Z invariance imposes certain restrictions on them, or more precisely on the generating functions. And what is remarkable is that actually one can derive these constraints explicitly. And this is what I'm showing on the next slide, namely that these constraints can be formulated in the following way. They require that this particular combination of the generating functions must be a modular form of the same weight which we had before. So how this combination looks like? So you see, you have just the original generating function plus certain correction term. And in this correction term, you decompose the D4 brane charge into some other charges, which all must be positive. And so this is equivalent to kind of having a bound state. So you sum of all possible bound states. And then you take a product of generating functions corresponding to constituents of your bound state and multiply by certain functions.